Okay, so I'm going to just go over a few pitfalls with the correlation coefficient, right? So I think most of you are probably aware of the correlation. So equation one is the formula for it, right? Notationally, most people write it as a lowercase r. So the correlation measures the strength of the linear relationship between two quantitative variables. So a key part of this is that people miss or they forget that it's meant to only measure strength of linear relationships, right? So that's one key point I'm going to emphasize in the next few slides. So we typically know, right, that if it's a positive value, if the correlation is positive, it's bounded between 1 and -1, right? And positive values indicate a positive linear relationship between the variables. So when we say positive linear relationship, means that as one variable increases, the other increases as well. Negative values of the correlation indicate a negative linear relationship. So a negative linear relationship means that as one variable increases, the other decreases. And the closer the correlation is to either 1 or -1, then the stronger the linear relationship, right? So the closer it is to 0, right, the weaker the linear relationship. Now, while the correlation is widely used, right, there are a number of pitfalls that some people may not be aware of, and maybe they kind of overlook and forget about these issues. So I'm going to be using this correlation applet. So let me just open this up. And I'll kind of use this applet to kind of just show some examples of what I'm going to talk about next. So, right, pitfall number one, right? So as I emphasized earlier on, correlation is a measure of linear relationship. So it only should be used if the relationship is linear and should never be used, never, if the relationship is nonlinear, right? So one thing you should always do, right, is to look at the scatter plot of your two variables first to see, visually inspect if a linear relationship exists, right? So for example, if you have a situation where, right, you clearly have a nonlinear relationship, then there's no point even bothering to calculate the correlation because, right, this doesn't matter if the relationship is not linear. So it only matters if, right, we have, right, so that's a positive linear relationship over here, right? So it is a positive, right, close to 0.8 linear relationship, and if it's negative, right, it means as one decreases, as one variable increases, the other decreases. So these are fine, right? So you should always look at the scatter plot first, right, to see if the relationship is linear. A high correlation, right? So very often people will read the data in and calculate the correlation, and they kind of feel happy if they see a high value for the correlation. Now, high correlation itself is not proof of a strong linear relationship, right? You can have a relationship that is clearly not linear yet still have a high correlation. So you kind of notice again, what should be done is to look at the scatter plot first and then assess, right, if a linear relationship exists. So right, a high correlation is not proof of a strong linear relationship because there are instances where you clearly have nonlinear relationships. So something like this, where the correlation is pretty high, right? So that's one example. Another situation, perhaps, right, this is pretty high as well, but this is more like a sine wave kind of shape. So the fact that this is close to -1 doesn't mean that we have a strong negative relationship. So again, same story, look at the plot first to see, right, if you have a straight line relationship. Right, so high correlation, not proof of strong linear relationship. And the opposite is kind of true. A low correlation is not proof of a weak linear relationship. Right, you could have a strong linear relationship that results in a low correlation, right? So kind of same, you kind of realize what I'm trying to get at. Always produce a scatter plot first to see if you have a straight line relationship. So you could have clearly a quadratic relationship. So you might, if you only take the correlation, you might say, hey, right, it's a low value, and so some people might say, oh, this is evidence that there's no relationship. Nope. Right, it's that, well, if you look at the plot, it's clearly a quadratic relationship. You shouldn't even bother looking at calculating the correlation in such a situation. Another example would be like the sine wave kind of relationship again, where right there's clearly a sine wave, but the correlation is pretty small. Right, so right a low value right of the correlation is not proof of a weak linear relationship. It actually could be from a strong nonlinear relationship. The other thing is correlation is sensitive to the presence of outliers. So the presence of outliers can distort the value of the correlation. So outliers, we generally define it as data points that are very different from the other data points. So for example, let's say we have kind of a strong linear relationship right with these data points, and then you have this outlier over here. Notice the existence and removal of these outliers. So with the outlier, correlation is negative 0.6. Without, correlation is close to 0.9. So the presence of this outlier severely distorts the value of the correlation. So you have to be very careful when you have outliers present. Some of the examples could be when you don't really have a linear relationship, perhaps. So it's pretty small, and then you have an outlier, you can make it pretty big again, right? So from no relationship to right weak linear relation to right a high value of the correlation. Some other examples. Again, not much of a relationship over here, and then you have that outlier over there. Another interesting one would be you might have clusters, and within each cluster, right? So this is a negative relationship. And then you have another similar looking cluster over here that looks like a negative relationship, but yet when taken together, these two clusters combined result in a positive correlation, right? So the existence of outlying data points could really influence the correlation. Okay, so in all of these instances, notice I have the same solution. So really, right, you should always produce the scatter plot first to visually assess if a linear relationship exists, right? So long story short, produce a scatter plot and then visually assess, right? Then should you then calculate the correlation and interpret the value of that correlation?